Hello everyone. In this video, we shall take a look at how we can use quantitative data to determine oxidation state changes. I would encourage all of you to download the worksheet that accompanies this video so that you can follow along. The link is in the description below. A central idea to redox reactions is that the number of electrons gained must be equal to the number of electrons lost. So this is the main idea we are going to apply in our calculations. Let me give you an example of a chemical calculations question that requires us to deal with oxidation states. In example 1, a solution containing 40 cm³ of 0.5 mol per dm³ VO2 plus ion was found to require 25 cm³ of 0.8 mol per dm³ iron 2 sulfate for complete reaction. Given that iron 2 plus is oxidized to iron 3 plus, which of the following ions could VO2 plus be reduced to? If we were to count, the oxidation state of vanadium in VO2 plus ion is plus 5. I'm also going to list down the oxidation state of vanadium in each of the following options. Plus 5 here, plus 4, plus 3, plus 2. So in other words, the question is saying vanadium is being reduced. Iron 2 sulfate is my reducing agent. Given this amount of reducing agent, what has vanadium been reduced to? These are the options. Okay. So we construct half equations again. Iron 2 is being oxidized to iron 3. This is our oxidation half equation. For the reduction reaction, I'm going to simplify it a little. I'm going to leave out the oxygen and just say that V5 plus, this is the starting oxidation state. It must have gained a certain number of electrons to become Vn plus. So N is the final oxidation state of vanadium. So if the final oxidation state is 4, so 5 minus 4 equals to 1, it must have gained 1 electrons. So we set up an equation in this manner. Alright? The very important rule is that the number of electrons here and here must eventually be the same. Okay, and we're going to compare that in a while. So let's make use of whatever we have in the question first. 40 cm³ of 0.5 mol per dm³. If we work out the number of moles, we will get 0.02 mole. Okay, and for the other side, 25 cm³ of 0.8 mol per dm³, it is also 0.02 mole. Using mole ratio, this would be 0.02 mole electrons because it is 1:1. Now here is 1:5 minus n. This is the coefficient. That means the number of moles of electrons here is 0.02, 5 minus n. Okay, the total electrons lost equals total electron gain. And I'm going to plug in 0.02 must be equals to this one. That means 5 minus n equals to 1, and therefore n equals to 4. So the final oxidation state is plus 4, and that means option B is correct. Okay, if you're feeling confident, you can go on and give the second example a try. I've already set up the two equations for you. Pause the video, and if you're ready, you can continue. In example 2, the sulfide ion is being oxidized to sulfate, and the oxidation state increases from plus 4 to plus 6 over here. They told us that the original oxidation state of the metal is plus 3. What has it been reduced to? Again, I'm going to simplify the half equation in this manner. The original oxidation state is plus 3. It has gained a certain number of electrons to get a final oxidation state of n. Let us calculate number of moles now. 50 cm³ of 0.1 mol per dm³, 0.005. And then using the one over here, we have 0.0025 moles. Work out our mole ratio, 1:2. That means this side is 0.005 and this side is 0.005 times 3 minus n. Applying the golden rule, total electron gain equal total electron loss. 0.005 3 minus n equals 0.005. 3 minus n equals to 1, n equals to 2. So the final oxidation state is +2. Remember your sign. Alright, feeling confident so far? Let's move on to example 3. In this example, potassium iodate is being reduced while iodide is being oxidized. We are going to set up our half equations again. In the reduction equation, iodate gains a certain number of electrons to form a species with a certain oxidation state which we do not know. The original oxidation state is +5. That means it must gain 5 minus n electrons. In the oxidation half equation, the iodide ion is being oxidized to ICl2. The oxidation state of iodide is -1, and over here it is +1. This means that iodide ions would have lost 2 electrons in order to gain an oxidation state of +2. Okay, now we try to put in number of moles based on the question. Number of moles of iodate, 0.0005 moles. Number of moles of iodide is 0.001 mole. Use your mole ratio to find number of moles of electrons. Then we use total electron gain equal total electron lost. So they say deduce the change in oxidation number. So we find that the final oxidation state is +1. That means the oxidation state would have decreased by 4. Let's go on to example number 4. Okay, we're going to set up our reduction and oxidation half equation. Chlorine molecules are being reduced, and we know that this is 4 mole, requiring 8 mole of electrons. Okay, in the oxidation equation, thiosulfate is going to become, we do not know what is the oxidation number here. Let's let it be N. So thiosulfate is being oxidized. Let's let the final oxidation state be N. Because we have 2 sulfur, we need to balance the equation. That also means when I have 1 mole of this, I have 2 moles of sulfur atoms. We are going to construct it in this manner. In thiosulfate, the oxidation state of sulfur is +2. That's the average oxidation state. So if we start off with sulfur having this oxidation state, it becomes here. Then it must have lost n-2 electrons. Because we have 2 moles of sulfur, this will be 2n-2. Using our golden rule, electrons gained equals electrons lost. 2n-2 equals to 8. That means n equals to 6. Therefore, our concluding statement, the oxidation state of sulfur in the product is +6. Alright, we've come to the end of the video. I hope you find this method useful. Till next time, thanks for watching.